Consider the following linear programming problem where a store wants to liquidate 200 shirts and 100 pairs of pants from last season. They've decided to put together two offers. We're going to call them Offer A and Offer B. Inside of Offer A, we're going to give our customer one shirt and one pair of pants, and we're going to sell that package for $30. Inside of Offer B is going to be a package of 3 shirts, a single pair of pants, and we're going to try to sell that for $50. Now, obviously, we're going to try to maximize our revenue that we're going to be bringing in, so let's create our maximization function. It's going to be P is equal to, let's say, 30A plus 50B, because each package A sells for $30 and each package B sells for $50. Next, let's go ahead and try to find some of our constraints. Since we only have 200 shirts, we can make the following first constraint, that A plus 3B must be less than or equal to 200. In other words, all of the packages A that I sell plus 3 times the packages of B that I sell have to be less than or equal to 200. I can't sell more shirts than what I have in stock. And similarly, it must be that A plus B is going to be less than 100 because we only have 100 pants. Now, the last couple constraints we have for our problem are going to come from the sentence where the store doesn't want to sell less than 20 packages of A and less than 10 packages of B. So here we have that A must be some kind of integer above 20, and B must be some kind of integer above 10. And here's the formulation of our linear programming problem. Next, let's go ahead and try to plot out our constraints so that we can see where our feasible region is. If we take our first constraint of A plus 3B is equal to 200 and set A equal to 0, we can solve for B by dividing by 3. That gives us 66.67. And next up, if we assume that B is equal to 0, that's going to give us A is equal to 200. Next constraint we want to get a handle on is A plus B is equal to 100. Of course, if A is equal to 0, we get B is 100. If B is equal to 0, we get A is 100. So I'm going to go ahead, I'm going to put a point here at 0, 100, and a point down here at 100, 0. And the last thing we need to do is just get our final constraints of A being bigger than 20 and B being bigger than 10 in. So next what we want to do is we want to take a look at our inequalities. Obviously with our 10 and 20, we're going to be going up or to the right of these. And for our green and black lines, we're going to be going down. So that implies that our feasible region has to be this region in here. And that's going to give us a fair amount of intersection points to consider. So we actually are going to have 1, 2, 3, 4 corner points to consider when we go to finalize our problem. So one of these corner points we can get at right away. We know that this one down here in the bottom left happens when A is equal to 20 and B is equal to 10. It's the intersection point of our blue lines. Next, if we scroll along our blue line where B is equal to 10, we're going to land on that other lower corner point. This is on our green line. So if we take A plus B equals to 100, and we make the substitution that B must be equal to 10, we can solve for A, and A here is going to be equal to 90. Now, similarly, if we start at that corner point 20, 10, and we slide up along that blue line, we're going to land on our black line. And our black line is represented with A plus 3B is equal to 200. In this case, we're sliding along the line A is equal to 20, so let's make that substitution. And that tells us that 3B must be equal to 180. If we go ahead and divide both sides by 3, we're going to get B is equal to 60. So we can mark that corner point with 20, 60. The last corner point can be found by determining the intersection of the green and black line. I have them written here already, so let's go ahead and use the elimination method. Let's take equation 2 minus equation 1. So a take away a is obviously 0. 3b take away 1b is 2b's. And 200 take away 100 is 100. Dividing by 2, we get b is equal to 50. And if a plus b are both equal to 100, it must be that a is equal to 50 in this case as well. So our final corner point is going to be 50, 50. All right, so I'm going to go ahead and start my preliminary analysis on the minimization function with the corner points 2060, 2010, and 9010. Obviously, 2010 is not going to be the maximal profit because we know that both 2060 as well as 9010 are going to bring in more profit than 2010. So let's determine just how much profit we're going to have at these two corner points. Here we can take 30 times 20 and add to it 50 times 60, and it's going to give us a profit of $3,600. If instead we sell 90 package A's and 10 package B's, what's going to be our overall profit? In this case, it's going to be $3,200. So this corner point definitely can't be the maximum. We have just that one final corner point to check, and that's going to be if we sell exactly 50 A's and 50 B's. So let's see, let's take our 30 times 50 and our 50 times 50 and see what our profit margin looks like here. If we are able to sell all of these packages, we would have a profit of $4,000, which is actually the largest profit we could possibly get in this question. So our conclusion is that in this case, we should try to aim to sell 50 of both packages.